Welcome to Lecture 4 in our third week of the course Analysis of a Complex Kind. Today we'll learn about the complex trigonometric functions, so the extensions to the complex plane of the sine and cosine functions. We have already extended the exponential function to the complex plane, so the question is, can we do the same thing for trigonometric functions? Now remember, e to the I theta was our shorthand notation for cosine theta plus I sine theta. Therefore, e to the minus I theta, well, you just replace theta with minus theta, it's cosine of minus theta plus I times sine of minus theta, but cosine is an even function, these are just our regular real value cosine and sine functions, so that's cosine of theta, but sine is an odd function, so sine of minus theta is minus sine of theta. Now look at these two identities. E to the I theta is cosine theta plus I sine theta, e to the minus I theta is cosine theta minus I sine theta. If I add these two things up, what I find is that e to the I theta plus e to the minus I theta is simply two cosine thetas. The I sine theta part cancels out because it has a plus sign here and a minus sign there. On the other hand, if I subtract these two equations from each other, I find that e to the I theta minus e to the minus I theta is 2I times sine theta, because now the cosines cancel out and the sines don't. But these two equations that I just obtained, I can solve them for cosine theta and sine theta by simply dividing by 2 or 2I. And what I get is that cosine theta is e to the I theta plus e to the minus I theta over 2, and sine theta is e to the I theta minus e to the minus I theta over 2I. And this is for the real value cosine and sine. The idea is now, well, now that I can talk about e to the I anything, it doesn't have to be just a theta, I could put a z there. Maybe I could just extend this definition to the entire complex plane, and that's exactly what we're going to do. The complex cosine and sine function are defined via cosine of z equals e to the iz plus e to the minus iz over 2, and sine z is e to the iz minus e to the minus iz over 2I. What is e to the iz, by the way? E to the iz, suppose z is x plus iy, so that's e to the I x plus iy. That equals e to the ix plus I squared y, which is minus y. So that would be e to the minus y, which is our regular real value exponential function, times e to the ix. You could rewrite this as e to the minus y times cosine x plus I sine x. And now we have expressed e to the iz in terms of purely real value functions. You could do the same thing for e to the minus iz, and so therefore cosine z can be expressed in terms of all real value cosine, sine, and exponential functions. And we'll do that later. Let's next learn about some properties of the complex cosine and sine functions. In particular, we want to compare those properties that we already know from real valued analysis to those that we can find for the complex equivalents. First of all, sine z and cosine z are analytic functions because the exponential function is an analytic function. The function z goes to I times z is analytic, and so you see a composition of those two functions right here. We're adding another analytic function and then dividing by 2. So by the rules of analytic functions, the cosine function is an analytic function, and similarly the sine function is an analytic function. Since they're analytic in the entire plane, they're in fact entire functions. For real valued z's, so if you plug in a z of the form x with no iy, so just z is equal to x, the complex sine function and cosine functions agree with the real valued sine and cosine functions, because in that case, I get cosine of z is equal to cosine of simply my x plus I times 0, and that's e to the ix plus e to the minus ix divided by 2, and that's the definition of our real valued cosine function. What's cosine of minus z? For the real value function, the cosine function is an even function. Cosine of x is equal to cosine of minus x. Is that still true for the complex cosine function? Well, cosine of minus z is e to the minus iz plus e to the iz, and I can just interchange these two terms on top here, because addition is commutative, and I see that this is equal to the cosine of z. Sine of minus z is e to the minus iz, I'm just plugging in a minus z for z up here, so e to the minus iz minus e to the iz over 2I. I can't just interchange these two terms because of this negative sign. So if I do interchange these two terms, I get an additional negative sign. So sine of minus z is minus sine of z. Just the same thing is true in real valued analysis. Sine of minus x is equal to minus sine of x. Sine function is an odd function, remains so in the complex extension. Furthermore, the addition properties for the sine and cosine functions still hold. Cosine of z plus w equals cosine of z cosine of w minus sine z sine w, and sine of z plus w is sine z cosine w plus cosine z sine w. How would you prove such a thing? I'll show you an example. How would you prove that cosine of z plus w is equal to cosine z cosine w minus sine z sine w? You would simply plug in the definitions and simplify. Let's do that. Let's start with the right-hand side, in fact. Cosine z cosine w minus sine z sine w. Here I wrote down the expression for cosine z, e to the iz plus e to the minus iz over 2. The same thing for cosine of w, minus sine z, e to the iz minus e to the minus iz over 2I, and here I have sine of w. I notice when I multiply these first two fractions with each other, the denominators multiply to 4. With the second two fractions, the denominators are 2I times 2I, which is negative 4 in the product. Together with this negative sign in front, I can cancel the negative sign from the denominator and make this negative sign into a plus. So the common denominator for these products of fractions is 4, and the numerators are e to the iz plus e to the minus iz, that's from this term right there, then e to the iw plus e to the minus iw, and now I have a plus. Remember from the I squared and this negative sign? Then I have this term, and finally this term. Now when I multiply through, I get a lot of terms. We're not going to talk through all of these terms. Just trust me, these are all the terms you get when you multiply through. For example, e to the iz times e to the iw, e to the iz times e to the minus iw, and so forth. But if I look at these terms carefully, I have an e to the iz, e to the iw right here, and there's another one right there. Together that gives me 2 e to the iz, e to the iw. I also have an e to the minus iz, e to the minus iw here, and another one right there. Together that gives me 2 of these terms. The rest, we get lucky. The rest actually cancels out. E to the iz times e to the minus iw, and here I have minus e to the iz, e to the minus iw. So these two terms cancel out. Similarly, e to the minus iz, e to the iw, and minus e to the minus iz, e to the iw, so these two terms cancel out. So everything simplifies. Now I have a 2 in the numerator, a 4 in the denominator. I can cancel out one of those 2's and make the denominator 2 instead, and end up by combining the exponents with e to the I z plus w plus e to the minus I z plus w over 2. Well, that's cosine of z plus w. That's what I want to show. So there's no ingenuity in here in this proof. It's literally plugging in the definitions and simplifying. further properties. Remember, the real valued cosine function is periodic with period 2 pi. Is that still true for the complex cosine function? Let's find out. What is cosine of z plus 2 pi? I use the definition and replace z with z plus 2 pi. But what is e to the I times z plus 2 pi? That is e to the iz times e to the I times 2 pi. What is e to the 2 pi I? That's equal to 1. So that's equal to e to the iz. In other words, this first term is simply e to the iz, and similarly the second term is simply e to the minus iz. And so I realized the cosine function is also periodic with period 2 pi, and similarly the sine function has the same period. Remember, in real analysis, sine squared x plus cosine squared x equals 1? Well, that's still true for the new complex sine and cosine functions. Sine squared z plus cosine squared z equals 1. How would you prove that? It's actually a very simple proof. You substitute w equals minus z in the addition formula for the cosine function. Let me simply demonstrate how to do that. The addition formula for the cosine function was cosine of z plus w, but we're going to make that z plus minus z, and that's my w, is equal to, the addition formula says cosine z, cosine w, which is minus z for me, minus sine z, sine w, which is minus z. Let's simplify both sides of the equation. Z plus minus z, that's simply 0. So this side of the equation becomes cosine of 0. The cosine of 0 is 1. On the right-hand side, cosine of minus z is the same as cosine of z. We showed that the cosine function is an even function. So this is cosine z times cosine z, which is cosine squared of z. On the other hand, sine of minus z is minus sine of z. So this minus sign can be pulled out and joins this minus sign in order to give me a plus. Altogether, sine squared of z. So that's how simple it is to prove that formula. Furthermore, sine of z plus pi over 2 gives us back the cosine function, just as it was the case for the real valued functions. Again, it's very simple to prove. You look at sine of z plus pi over 2 and plug z plus pi over 2 into the definition of the sine function. So wherever you see a z, make it a z plus pi over 2. So sine of z plus pi over 2 then equals e to the I z plus pi over 2 minus e to the minus I z plus pi over 2 divided by 2i. And what is e to the I z plus pi over 2? Again, we can pull that apart. As we did earlier, that is e to the I z times e to the I pi over 2. What is e to the I pi over 2? E to the I pi over 2 equals I. So in other words, this is I times e to the I z. Similarly, the second term is minus I times e to the minus I z because I have an e to the minus I pi over 2, which is minus I. This simplifies because I have an I in the denominator as well. See this I right here? This I in the denominator cancels out with this I and that I. These two negative signs make a plus. I'm left with e to the iz plus e to the minus iz over 2, which is cosine z. What are the zeros of the sine function? We know the zeros of the real valued sine function. The real valued sine function looks something like this. It goes to the origin and is equal to 0 at pi, 2 pi, 3 pi, and so forth, negative pi, and so forth. Are there additional zeros now that we've extended this function to the complex plane? Let's find out. Remember, sine z is e to the iz minus e to the minus iz over 2i. If we want that to equal to 0, then we need the numerator of this fraction to be equal to 0. So e to the iz needs to equal e to the minus iz. Remember, we proved that e to the z is equal to e to the w if and only if z minus w is a multiple of pi I times 2. We proved this in our lecture about the exponential function. So e to the iz is equal to e to the minus iz if and only if their difference, in other words, iz minus minus iz, is of the form 2k pi I for some k in the integers. But iz minus minus iz, that's 2iz. So 2 iz's needs to be equal to 2k pi I. I can cancel out a 2, I can cancel out an I, and this reads z needs to be of the form k pi, where k is an integer. Those are exactly the zeros that we already knew of. So the sine function does not gain any extra zeros by extending it to the complex plane. It's never going to be 0 elsewhere. It's only 0 on the real axis. Similarly, we can show that the cosine function is 0 only when the real valued cosine function was 0, namely at the points pi over 2 plus k pi, where k is an integer. Now we showed that the sine and cosine functions are analytic functions, so they must have derivatives. What are these derivatives? The derivative of the sine function is simply the derivative of e to the iz minus e to the minus iz over 2i. 2i is a constant that we multiply with. It can go to the side. In other words, we only need to take the derivative of the numerator. The numerator consists of two functions, each of which we can differentiate separately. In other words, we need the derivative of e to the iz and the derivative of e to the minus iz. Let's look at the derivative of e to the iz. We found the derivative in general of a function e to the a times z, and found that was a times the derivative of e to the az. So in this case, this is going to be I times e to the iz. That's right here. The derivative of e to the minus iz is found similarly. We multiply with this constant minus I, e to the minus iz. When we simplify, we see there's an I here, an I here, an I here. They all cancel out. Minus minus gives me a plus. So I'm left with e to the iz plus e to the minus iz over 2, which is cosine z. Just like it was the case for the real valued sine and cosine functions, the derivative of sine is cosine, and similarly, the derivative of cosine is negative sine. Finally, it is possible to express the complex sine and cosine functions solely in terms of the real sine and cosine and that real hyperbolic sine and cosine. Let me quickly show that to you. Sine z is sine of x plus iy. We could view this x plus iy as the sum of two complex numbers. One of those complex numbers is x, the other one is iy. In other words, we are allowed to use the addition formula here. So this becomes sine x, cosine iy, plus cosine x, sine iy. What is cosine of iy? We need to plug in iy in the cosine formula and get its e to the I times iy plus e to the negative I times iy over 2. And then back here we do the same thing with the sine function. E to the I times iy minus e to the minus I times iy over 2i. Let's see what we can simplify. I times y, that gives me a minus y. And here I times y times negative 1 is just e to the y. And back here the same thing happens. If I rewrite this, I find that this first fraction is e to the y plus e to the minus y over 2. And the second fraction, I have an I in the denominator. If I bring the I into the numerator, 1 over I is equal to negative I. So I can bring that into the numerator at the expense of a negative sign, but I'm going to use that negative sign to flip these two terms with each other. So I can now write e to the y minus e to the minus y over 2, and an I here in the front. But now I'm left with sine of x. This is the hyperbolic cosine function, cosh of y. plus I times cosine of x times sinh of y. Or you could also leave it the way it was in the previous line if you don't like to use caution sinh. And have another way of actually evaluating sine of z in terms of purely real valued function, namely the sine of x and the exponential function and the cosine of x, and the exponential function of y and minus y. Similarly, you can find that cosine of z is cosine of x cos y minus I sine of x sinh y. Next up are some amazing properties of analytic functions. Here's an example. If f is an analytic function in the domain, and you write it as real part plus I times imaginary part, use the real part, v is the imaginary part, and suppose the real part u is constant throughout the domain, then f itself must be constant. There's no way to have an analytic function where only the imaginary part varies. If the real part remains constant, the imaginary part has to remain constant as well. Real and imaginary part are not independent of each other, they're tied together closely, and that's what gives analytic functions some of their amazing properties. This is what we're going to study in the next lecture.